Hello and welcome to Tech Simplified TV. This is the third episode on interconnect in physical design. Today we will start from where we have concluded our last episode. That is discussion about considering inductance parasitic in delay modeling. Today we will discuss about on-chip inductance and impact of on-chip inductance in state-of-art ICs. Today we will try to understand on-chip inductance, their impact on device performance, and the methods by which we can control their impact. So if you are interested, stay tuned till the end of the video. So let's take a look at the pointers we are going to discuss in today's episode. First, how on-chip inductance becomes significant. Second, interconnect model mapping with technology node, loop and partial inductance, transmission line model, a small recap, dependence of impedance on frequency, impact of on-chip inductance, first, second and third slide, then difficulties with inductance, then techniques to minimize on-chip inductance, first two slides, then techniques to minimize on-chip inductance, more two slides, and significance of termination, and finally modeling of interconnect at high frequencies. Now let's move to the first slide, how on-chip inductance becomes significant. On-chip inductance effects have become increasingly significant because some global signal and clockware have large widths and thicknesses at the top level of metal to minimize delays. To minimize the delay, some top level metal layers like global signal and clockwares, their widths and thicknesses are kept wide. They have larger widths and thicknesses, so these decrease the resistance of the wires, making their inductive impedance comparable to the resistive part. Now, impedance of metal interconnect is expressed with Z equal to R plus J omega L. If resistive part is less and at increasing frequency, this part is comparable to R. So, when one part of impedance is comparable to the other part, we have to consider the both. We cannot any longer ignore this part. Next, as the clock frequency increases and the rise time decreases, electrical signals comprise more and more high frequency components, making the inductance effects more significant. Clock frequency increasing and electrical signals, they are comprised of more high frequency components, and from this first point, this frequency portion is increasing, so inductance part is increasing, so we cannot ignore inductance effects anymore. And this is a table. It's showing over the years how frequency has increased from 1.25 gigahertz in 1999 to 13.5 gigahertz in 2014. Signal transition times become more shorter comparable to the signal time of flight, and devices become faster. So speed has increased, devices become more, their dimensions have become smaller, their switching speed has increased, so devices become faster and signal transition is becoming faster. With the increase of chip size, it's fairly typical that many were long and run in parallel, which increases the inductive crosstalk and delay. Just look at our smart devices, our consumer electronics. Our device is as smart as much its processor or their processing unit is smart. So we want more and more complex operation in our devices or in our consumer electronic devices. So just to cope up with that, the chips are increasing in size and they are accommodating more and more devices into the same chip. So what is actually happening? The wires or interconnects, they are connecting. There are many operating blocks are there on the same design, same system, and they are connected for complex operation. So wires are running for longer length and they are running in parallel. So that increases the inductive crosstalk and delay. And with the push of performance, some low resistivity metals like copper, they have replaced aluminum in order to minimize the RC delays. That increases inductive effect more because resistance becoming less. So this portion is again becoming more significant compared to R. So that's a point. Now let's move to the next slide. Interconnect model mapping with tech nodes. There is a diagram. It's showing two pieces of interconnects. And just to remind us that an interconnect is not just a piece of interconnect or piece of metal. It's basically capacitor, resistors, and inductor. So this is the model for the first piece of interconnect, and this is the C2, R2, L2 for the second piece of interconnect, and they are moving parallel. There is a mutual capacitance and there is mutual inductance, what we are saying. So this is the scenario. And if for interconnect models, look, the technology node is moving towards smaller size. Resistance was initially ignored, then lumped, then distributed, and finally it's distributed. And capacitance models also consideration also is changing from area capacitance to area and 2D fringing, then 2/3 dimension fringing, then lateral coupling. And now when it's less than 25 micron, its lateral coupling is dominant. And inductance, first up to this it was ignored, and now it's become important. And circuit model, lumped C, lumped RC, distributed RC, and distributed RLC. These are the circuit symbols. So we are done with this slide, and let's move to the next slide. Loop and partial inductance. So loop inductance is defined as the induced magnetic field in the loop by the unit current in other loop. This is a loop, J loop. Current Ij is flowing. So this flow of current in this J loop is inducing a magnetic flux in this I loop where I current is flowing. So L, that is induced loop inductance from one loop to another. It's a loop. So magnetic flux is induced from one loop to another. This is the loop inductance, where psi ij represents the magnetic flux in loop I due to current ij in loop J. Now, problem with loop inductance. Calculation of loop inductance require knowledge of return paths. When we are considering loop inductance, we need to know the return path because it's a loop. As long as we do not know the return path, the loop is not closed. Calculation of loop inductance is incomplete. It's really difficult to determine return path for on-chip interconnects explicitly, since there is no ground plane. So it's calculating this one is return path calculation is tough. Almost everywhere coupled to many wires, and there are multiple return paths. Because it's a complex 3D geometry on the level of interconnect. So many interconnects running parallel, up, down, both sides. So it's a complex 3D geometry of interconnects. So determining a single return path is difficult. Almost everywhere is coupled to many wires, and we will see that this inductance property is basically it's a long range effect. For capacitance, we can consider the nearby elements, but for inductance, the effect decreases very slowly with distance. So almost everywhere coupled with many wires. So there is a complex 3D geometry, and at that situation, confirming a return path is difficult. So what we do, we take partial inductance in consideration. What is that? It was proposed by A. Rueli, the partial element equivalent circuit method, PEC method. This is based on partial inductance. Partial inductance is the portion of loop inductance for a segment when its current returns via infinity. So it calculates based on that the return path is infinity. It returns from infinity. It can be directly applicable to circuit simulator like SPICE. Because ultimately we need to use them in tools. All these mathematical calculations and everything, we don't, with this complex geometry and tight time to market, we cannot do all these complex calculation by hand. So tools have to do it. So this is the model. We will talk about it later. And now properties of partial inductance. Partial self and mutual inductance are based on geometry only. They may be solved by using 2D and 3D field solver. 2D and 3D field solver, basically they calculate that Maxwell's equation. They solve Maxwell equation. The return path of the current loop may be determined through SPICE simulations. The partial self and mutual inductance may be frequency and proximity dependent. These are the properties of partial inductance. So we are done with this slide, and let's move to the next slide. TL model, a recap. We have discussed about transmission line model in last episode. It's just a small recap, because after that we will talk about termination of transmission line. Inductance also distributed over the wire like R and C, and the transmission line model is at high frequency and state of art devices. It's a almost most accurate approximation, and signal propagates as a wave. These are the equations, and for insulating material, leakage conductance G is 0. So wave equation that finally we get this equation where R, C, L, everything is per unit length because it's distributed per unit length value. And for lossless transmission line, R equal to 0, that is resistance 0 with step input propagates with a speed root over 1 by LC. So from there we get delay per unit length EP. This is the LC. It's just a small recap. We have discussed it in detail in last episode. And this is the wave form. This is the input waveform, and transmission line. This is lossless transmission line, and this is lossy transmission line. Just a time shift. If there is lossless transmission line, not any part of the input signal is lost, almost transmitted like as it is. Although for lossless, its shape is changed. Some portion of the signal is lost. So we are done with this slide, and now we will move to the next slide. Dependence of impedance on frequency. In a circuit with multiple current paths, the distribution of the current flow is frequency dependent. When a circuit have multiple current paths, distribution of the current flow become frequency dependent. How? At low frequency, current path is determined by resistance of the path. At high frequency, current path is determined by the inductance of the path. Low frequency, where we have that Z equal to R plus J omega L. At low frequency, this part is very small. R is much greater than Z. So, in forward current is going when return path is dependent like this, that low R, low resistance path, most of the current return through low resistance path, and a small portion of it returns through high resistance path. Although what happens at high frequency is completely different. For high frequency, R is much less than J omega L. So, for return current, it's like most of the current return to a low inductive path and smaller part of the current returns with low resistance and high inductive part. And these are the current distribution equation. At low frequency, the equation is governed by R2 because this portion is negligible, and at high frequency, the equation is governed by L value because this portion is considerable and this is negligible. So this effect is primary source of inductance variation with frequency in integrated circuits. So now let's move to the next slide. Impact of on-chip inductance. So any current passing through a conductor creates a magnetic field. This magnetic field then induces a parasitic current either on the same metal, that is self-inductance, or on another metal crossing the magnetic field, that is mutual inductance. And we focus on the, if we focus on the resistance and inductance, we can express interconnect impedances. And just see impedance, omega L part is increasing like that and R is increasing like that with frequency. And now skin effect. It's a high frequency phenomena. As frequency increases, the current tends to flow closer to the conductor surface or skin, between the outer surface and a level called skin depth. At low frequency, it's homogeneous. At high frequency, no more homogeneous. It flows between outer surface and a length called skin depth. So skin depth is defined as the depth where the current density is just 1 by E, that is about 37% of the value at the surface. So from surface, the current density is decreasing, and when at each depth it becomes 1 by E, that is 37% of value at this surface. This is called the skin depth. And just look at this graph. Skin depth is decreasing with frequency. That means more the frequency increasing, the skin depth is decreasing. So more and more current is concentrated towards the surface. Skin effect increases the resistance parasitics of a conductor at high frequency. They also lead to frequency dependent value for the effective inductance and resistance seen by the current. Such effects must be included in the parasitic extraction to achieve accurate results. So skin effect not only increasing the resistance parasitics of a conductor, also changing the effective inductance and resistance seen by the current. Here we are done with this slide, and let's move to the next slide. Impact of on-chip inductance. Now proximity effect. So when two or more conductors carrying AC are close to each other, then distribution of current in each conductor is affected due to varying magnetic field of each other. The varying magnetic field produced by AC induced eddy currents in the adjacent conductor. When the nearby, this is important, when the nearby conductors carrying current in the same direction, the current is concentrated at the farthest side of the conductor. When current, these are two conductors adjacent to each other, current is flowing in the same direction, so current concentrated towards the farthest. When the nearby conductors are carrying current in opposite direction to each other, the current is concentrated at the nearest part of conductors. This effect is called proximity effect. So opposite direction, current is, suppose it's flowing this direction, it's coming this direction. So these are the close, concentrated at the nearest. So this side, close to each other. Current is flowing in opposite direction, current is concentrated here in the nearest part, and when it's in the current flowing in both the conductors in the same direction, the current is concentrated on the farthest side. This is proximity effect. The proximity effect also increases with increase in frequency, and effective resistance of the conductor is increased due to proximity effect. So we are done with this slide. Now we are moving to the next slide. Difficulties with inductance. First is it depends on frequency. Second, inductance of wire requires knowledge of return path with this complex geometry. The VSS or VDD closes loop for each piece of interconnection. The return path is decided by signal pattern and interconnect geometry for a large range. Often a return path is not easily identified, particularly at layout stage. It's not necessarily through the silicon substrate. And silicon substrate cannot be considered as ground plane as the resistivity of the doped substrate layer is very high compared to the metal, and the substrate is too far away from the high-speed buses or clock wire. If we take the cross section, so these are the top metal layers here, then at somewhere here it's the substrate. So basically from top level wires, substrate, these are quite far. This is one reason, and another is silicon substrate, although it's doped, lightly doped, still its resistivity is much higher compared to the metal. So it's not a very feasible solution. Mutual coupling between wires decreases very slowly. Magnetic fields die out at a far distance as compared to the electric fields. It's another problem because for capacitance, what we do that considering near neighbors, which is enough for capacitance, is not enough for inductance. We consider only near neighbors. Mutual inductive coupling between wires decreases very slowly. We have to consider that quite far wire also. Calculations become complex. Reason of concern for high frequency designs because it frequency dependent. Inductance is not scalable, and inductance results in many high frequency poles and zeros, making reduced order model approximation difficult. We always make a trade-off between accuracy and time. We have to make it as much accurate possible, and we have to complete it within time also. A very accurate, at the same time very complex methodology to solve it, to model it, is not always a very viable solution. And inductance in the equations or in the when we solve in the system equations, inductance results many high frequency poles and zeros. And while discussing about Elmore delay, we said that Elmore delay might not be a very good approximation, although it works really well because it's quite simplified and it gives us first order solutions. Presence of multiple poles and zeros make the situation tougher because reduced order model approximation become very tough. So inductance creates quite a difficult situation in modern ICs. Now let's move to the next slide. Minimizing on-chip inductance. Dedicated ground wires. Increase the mutual inductance by making the signal wire and its return path to be as close as possible. Decrease the self-inductance by increasing the width of return path or by adding one or more ground wire between signal wires. First, it gets a return path and it increases the mutual inductance and decrease the self-inductance. Next method is differential signaling. This method has high signal to noise ratio due to common mode noise rejection. However, requires double the number of signal paths as compared to single-ended transmission network. The transmitter at the near end of the network converts the single-ended signal into an opposite polarity differential signal, while the receiver at the far end of the transmission line converts the differential signal into a single-ended form. So first, this is the single-ended input. When the transmitter get it and transmit it, it transmit in the original one and change the polarity, transmit both. That's why we are talking about that it requires double number of signal paths. And at receiver, it again convert it and make it a single-ended input, although it has a benefit of high signal to noise ratio. Now let's move to the next slide. Splitting of wires. There are two ground These are two ground path, and this is signal wire. Splitting a wide wire into several n parallel wires of about 2 skin depths with each may reduce the total reactance by a factor of n. That's a method. Another method is continuous power or ground plane. When signal travels a long distance for a current return without planes nearby, that causes inductive coupling. So ground and VDD, continuous power or ground plane, greatly reduces the coupling because it's provide a return path. This impedance control low loss line, these are the multi-layer interconnect, and this is substrate. These lines are closer to the interconnects. That is a viable solution. Now let's move to the next slide. Buffer insertion. With inserted buffers, inductive coupling decreases slightly faster than linear rate. Each segment becomes more RC line than RLC line because L per segment scales down at a rate faster than RLC. So we can insert buffers to reduce inductive coupling, and that reduce inductive coupling slightly faster than a linear rate. Now shielding. Another method. Shielding techniques are widely used to reduce capacitive and inductive coupling. Isolates an aggressor or noisy line from sensitive neighboring lines. Increases the noise tolerance of a sensitive line. The voltage of the shield line typically doesn't switch. By inserting a shield line between signal lines, changes in the effective interconnect capacitance is significantly reduced, resulting in less delay uncertainty. Inductive coupling and self-inductance can also be reduced by inserting shield lines, since the shield line provides a nearby current return path. So here a signal line is on both sides shield line, and between signal line, and here shield line is in between two signal line. So it actually reduces coupling, and obviously the delay is decreased. Let's move to the next slide. Now termination. We said that we will discuss about transmission line termination. At this high frequency, obviously the wires behave as transmission line, and the behavior of a transmission line is strongly influenced by termination of line. The termination determines how much of wave is reflected upon arrival at the wire end. It must be R. This is expressed by the reflection coefficient rho that determines the relationship between the voltages and currents of the incident and reflected waveforms. Rho equal to R minus Z0, R plus Z0, where R is termination resistance and Z0 is characteristic impedance. So if R equal to 0, if the transmission line is terminated with the characteristic impedance, rho becomes 0. That means no part of the incident wave is reflected back. That's a perfectly matched termination. And when R is much greater than characteristic impedance, rho becomes 1. So the circuit will behave like it's open circuit termination. The whole part of the wave is returned. So the total voltage waveform after reflection is twice the incident one. And if R is 0, that is short circuited. The total voltage waveform after reflection equals to 0. Rho becomes minus 1. The total voltage waveform after reflection becomes 0. These are 3 typical cases. Now let's move to the next slide. Significance of termination. To reduce the coupling noise at the inputs of victim receivers, different termination methods are used, like shunt RC, series R, shunt series R, and shunt C, series R termination and diode termination. There are different types of termination, and each of them have their own advantages. Depending on the usage, we select them. And termination is really important to prevent ringing effect when signal or data traveling long path. Ringing is generated on the transitions of digital signals when a portion of the signal is reflected back down to the line due to a mismatch between the line impedance and terminating impedance. We know when it's perfectly matched, no part will be reflected back. If there is a mismatch, then obviously a part is reflect back. And if the mismatch, kind of a similar mismatch, is at the driving end, will re-reflect a further portion. Like here, if this is the input driver, it has a characteristic impedance. Driver also has an impedance, and if it's not matched, then again a part of it will get reflected back. This kept on happening. This creates the ringing effect, and look, it gives a oscillation kind of structure to the waveform. That's not desired one. The amplitude of the ringing depends on the degree of mismatch at either end of the line, while the frequency depends on the electrical length of the line. So how much it's mismatched depends on that amplitude of the ringing. So we are done with the slide. Now let's move to the next slide. Now finally, modeling of interconnect at high frequencies. So these are some models we use. At high frequencies, circuit dimensions become comparable to signal wavelengths, and it's not always possible to identify discrete parasitic element. There are some models used to extract parasitics at high frequencies. Field solver, we already mentioned it. Actually, field solver solves Maxwell's equation. Finite element method, moment method, boundary element method, finite difference time domain method, transmission line matrix, partial element equivalent circuit or PEEC method. These all are used. We already have mentioned about PEEC method. So these are standard methods used to solve this, and the EDA tools use different models inside them. So these are the basically models used to solve the equations and to get the parasitics at high frequencies. Today we will conclude here. Today we have discussed about on-chip inductance. So we will conclude here, and thank you for watching up to this point. Don't forget to like, share and subscribe. In case you have a dislike, please put it as a comment, and if you have a query or question, also put it as a comment. Thank you again, and bye for today.